In this lesson, we're going to talk about power functions and polynomial functions. So let's first of all discuss what we mean by a power function. So here's the definition of a power function. So a power function is a function that can be written in the following form. So here's the form. So it's f of x equal k times x to the p power. Now there's a couple of characteristics about p and k, and here they are. So k and p must be real numbers, and k, remember, is called the coefficient. So when writing a power function, it's always best when you see this to actually write it out yourself. So it'll be some real number k, so that's going to be your real number, times the variable, and normally the variable will be x, so this variable must correspond with what you have inside the parentheses here, raised to some real number. So k and p are real numbers. All right, so remember what a real number is. So here are examples of real numbers. So these are real numbers. So for example, an integer, a positive integer, is a real number. A negative integer is a real number. 2.7 is a real number. A fraction, 21 over 8, is a real number. Now notice all these real numbers here are rational numbers, okay, rational numbers, but a real number can also be irrational, like the square root of 10, pi. So all those are examples of irrational numbers here and rational numbers. So all those are examples of real numbers. So make sure you understand or you remember what a real number is. So these are irrational numbers. Irrational numbers. So a real number is either rational or irrational. Okay, so any function that's written in the form some real number times x to the real number power is called a power function. So here's some examples of power functions. Okay, the first one, 3x to the 7th. And I want you to notice that a power function only has one term. One term. Notice each of these will have just one term. So notice the coefficient 3 is a real number, and the exponent is a real number. Here's another example. H of x equals negative 1/2 times x to the 2/3 power. Coefficients are a real number, it's negative 1/2, and the exponent's a real number, 2/3. 3, k of x equals pi times x to the negative 2nd. The coefficient pi is a real number. It's an irrational number, but it's still a real number. And the exponent, negative 2, is a real number. So all these are examples of a power function. So f of x equals 8.7 times x to 2 and 1/2 power. Now, number 5, some students get confused about 5. So don't let that confuse you. So in number 5, you have g of x equals 3x times 2x to the 5th power. And remember we said that based on this definition, you have one term, right? Well, remember, so you know how to deal with this. When you multiply it like bases, x times x to the 5th, what do you do to those exponents? You add them up, right? And then you also know how to multiply 3 and 2 together. So basically, don't let this throw you off. This can be simplified into a one-term expression. Well, this is one term. It's just written in different factors. But don't let this confuse you. This is a power function. It is one term. It's just written in different factors, as different factors. But I want you to notice that this is actually equal to 3 times 2 is 6. X to the 1st times x to the 5th is x to the 6th. So see, real number, real number. All right, so don't let those throw you off. And then number 6 throws people off as well because they see that cube root of x. You have to remember something from a previous course when you dealt with rational exponents. So recall when you dealt with rational exponents from a previous course. And that's this. When you have, let's call it, let's use the variable x. X to the a divided by b. X to the a divided by b. So you see how I have x to the 2/3 here? That's a real number, right? So this is a power function. So whenever you have x to the a divided by b, you can write that as a radical. So be the b root. So this denominator is your index times x to the a power. All right, so x to the a divided by b is the b root of x to the a. So you learned this in a previous course. So when I come over here, I want you to notice that, and I'll put the cube root of x here. So the cube root of x, by this definition here, remember this is x to the first now, so it's really x to the 1 divided by 3. So 3 is your index, 1 is your exponent. All right, so notice 1/3 is a real number. So don't let the, when it's written in radical notation, don't let that throw you off. This is really 4 times x to the 1/3. So 1/3 is a real number, 4 is a real number. All right, so there are some situations where you may have to think a little bit further about what you see to make sure that what you have is really a power function. And then number 7, don't let number 7 throw you off either. You've had something like this in a previous course, -8 divided by x to the third. So remember the definition of a power function says this: f of x must equal some real number. Let me write it right here. Some real number times x to a real number, right? But you don't see it written like this. But this is, or this can be written in that form. So you got to remember when you dealt with negative exponents. So recall that if you had, let's say, x to the negative third. So remember, when dealing with x to the negative third, you can always write that exponent as a positive exponent by writing it as 1 over x to the third. So remember your rule with negative exponent rule, a to the negative b is 1 over a to the b power. And that's what you see here. So -8 divided by x cubed is really -8 times x to the negative third. Okay, so x to the negative third is 1 over x to the third. All right, so this is a power function because I can write it in that form. I can write it in this form right here. K, which in this case is -8, times x to the negative third power. So this can be written in that form. This right here can be written in this form. So 4 times x to the 1/3. Okay, so that right here can be written in this form. Same thing here. This can be written in this form. So it turns out that k would be 6, 3 times 2 is 6, and p would be 6 as well. 5 plus 1 is 6. Because when you multiply like bases, you add exponents. All right, so that was a definition of the power function. Now let's look at the next page. All right, so the next page are some examples. It says determine if the following are power functions, and we're just going to write yes or no. So in H, you have -x to the 7th plus 2x cubed. So is that a power function? Yes or no? The answer is no, right? Because remember, a power function only has one term only. So and that's it. And this has 2 terms, right? And you can't combine those because those are not like terms. So this is no. So the answer is no. Okay? So there's no way that this can be written in one term. All right. Number 2. So we have h of x equals 3x squared plus 2x divided by x to the 4th plus 5x. So is that a power function? And the answer is no as well. All right, so this is a rational function. And I want to remind you, I want to say this as well. Let me go back to this right here. So this right here is a rational function. Okay, and notice that this rational function, so rational function is where you have a fraction, which is 8 here, divided by another fraction. So that's a rational function. And it can be written in this form, which is a power function. This is also a rational function, but it cannot be written in this form. So the answer is no here. All right. Is this a power function? Yes, it is. Okay, that's an easy one to see, right? So your real number 7/4, your coefficient 7/4, and your exponent's a real number as well. So the answer is yes there. Let's see what we have next. Again, don't let that throw you off. So is that a power function? Yes, it is, because look, I can use properties of exponents to help me. So 1/2 times 3/5, 1/2 times 3/5 is 3/10. And then x to the 5th times x to the 1/2 is x to the 5½ power. When you multiply like bases, add exponents. 5 plus 1/2 is 5½. So you have a real number as your coefficient, and you have a real number as your exponent. So the answer is yes here. Okay, so just remember, you need to look at this and see if you can write it as a power function. E, is that a power function? Be careful there. So remember, a power function says this. You have to have some real number, and it could be 1 as well. And your variable must be your base, and your exponent must be a real number. See, this is not what you have here. Your exponent is a variable. That's not a real number. Your base here is a real number. So your base has to be the variable. So this is not a power function. In fact, probably next week or the week after, you're going to learn that this is an exponential function. So this is an exponential function. And so an exponential function cannot be a power function because the way that the expression is written. So in an exponential function, your exponent is the variable. In a power function, your exponent is the base, and your exponent here is the real number. So in a exponential function, your base is a real number. In a power function, your base is the variable. Okay. We already talked about that. You know you can rewrite this, right? So don't let this confuse you. You know you can rewrite this as -8 times x to 1 divided by 7. You learned that in a previous course. The idea of those rational exponents. So a rational exponent can be written as a radical. So the answer is yes here. And G, we already talked about that. You can write that as 6 times x to the -4th. All right. So real number, real number. So the answer is yes. All right. So that was that example. All right. So that was number 1 for that example. All right. So now we're going to look at polynomial functions. So we know what a power function is. Now let's talk about what a polynomial function is. So these are examples of polynomial functions. So here's one of them. G of x equals 3 times x to the 7th. Notice you have one term, right? H of x equals 2/3 x to the 4th minus 3x squared plus 5. Number 3, k of x equals 2 pi x to the 6th minus the square root of 5x to the 4th plus 3x cubed plus 5x to the 1st, and then your constant, right? All right, so those are examples of polynomial functions. Now, there are certain characteristics that makes these three a polynomial function. So let's look at that. All right, definition of polynomial function. A polynomial function is a function that can be written in the following form. So here's the following form. All right, so don't let this throw you off. It looks weird, right? But don't let that throw you off. So notice that these are terms here. A n x to the n, a sub 3 x to the 3rd, a sub 2 x to the 2nd power, a sub 1 x to the 1st, and then your a sub 0, which is your constant term. We call that the constant term. So these are terms, though. All these are terms. So a polynomial function is made up of terms. And notice these are all terms, right? One term. This has 1, 2, 3 terms. This has 1, 2, 3, 4, 5 terms. All right, so it's made up of terms. But let's talk about those exponents. Now listen carefully about the exponents. So the exponent of a polynomial function, listen carefully. So where n is a non-negative integer, so n must be an integer and it must be non-negative. So what does that mean, a non-negative integer? Well, that means this. That means that n is an integer. I'm sorry, let me write it this way. N is a positive integer, or 0. N is a positive integer or 0. That's what this means. N is a non-negative integer, means n is a positive integer or 0. Now remember, n, if you look at this, n are these exponents. So n is the exponent. So now I want to go back to those three examples and show you something. All right, so remember, n must, in a polynomial function, your exponent must be a positive integer or 0, right? That's all it can be. So let's look at those examples again. Look at this exponent. That's a 7. That's a positive integer. Look at these exponents. 4, 2. Now, let me remind you something about this constant 5. All right, so let me remind you about something. So you remember one of the properties you learned in a previous course, and even we talked about it in this course as well, is that zero exponent rule. Zero exponent rule or property. And that's this. When you have x to the 0 power, that's equal to 1. Okay? So you see this 5 right here? I can write 5 as 5 times x to the 0 power. And then, because that's 5 times 1, and 5 times 1 is 5, right? So all these constants, the 5, the -2, I can write with a variable as long as I put 0 there. All right, so when I wrote this, h of x here, I can write it like this as well. H of x equals 2/3 x to the 4th minus 3x squared plus 5x to the 0 power. And so remember that definition right here where n is a positive integer 0. See that? 0. That's this right here. Okay? 0. Because x is 0 is 1. 1 times 5 is 5. And then the same thing here where I had k of x. So I know I can write k of x as 2 pi x to the 6th minus square root of 5x to the 4th plus 3x cubed plus 5x minus 2x to the 0. All right. So notice that in all of those examples, though, all those examples, my exponents were positive integers or 0. Positive integer, positive integer, positive integer, 0, x to the 0. Positive, 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 1, x to the 0, so 0. Okay? All right. The other thing is this. Each AI, now when I say AI, I mean those coefficients. The coefficients, an, a sub 3, a sub 2, a sub 1. Each of those AIs, and even the constant here, each of those AIs is a coefficient and can be any real number other than 0. All right? So each of those can be any real number. Doesn't have to be an integer, could be any real number. Any of those real numbers that we talked about earlier. Okay? All these are real numbers. So all these coefficients, notice the coefficient here is 2 pi, that's irrational. Square root of 5, that's irrational. 3, that's rational. 5, -2. 2/3, that's a real number, that's rational. -3, 5, and so on. So all those coefficients can be any real number. It is just the exponent. It's the exponent for a polynomial function that must be a positive integer or 0. Okay? All right. Now, and so we talked about these terms. So all of those AI, XI, all of these right here are called terms. So when you look at the definition, this is a term, this is a term, this is a term. So all these terms are separated by that addition symbol. Say plus a term, plus a term, plus a term. Okay? All right, now in words, let's look at this. In words, a polynomial function consists of either 0 or the sum of a finite number of non-zero terms, each which is a product of a number and a variable raised to a non-negative integer power. So in other words, each of those terms here, each of those terms is a finite number. Okay, finite number means you can count them. 1, 2, 3, 4, 5. 1, 2, 3. I can count them. 1. Finite number. I can count those. So which is a sum of a finite number. See the sum? Plus, see this? Plus the negative square root of 5, plus 3x cubed, plus 5x, plus a -2. All right, is a sum of a finite number of non-zero terms. So non-zero terms means means that the coefficients are not 0. All right. Now, notice though, you can have a polynomial function consisting of 0. So in other words, this right here means this. F of x equals 0. F of x equals 0 is a polynomial function. This is a polynomial function. We also call this a constant function, and we talked about that in a previous lesson. That's also called a constant function because there's no variable attached to it. Constant function. In fact, just to let you know, f of x equals 3 is a constant function as well, and that's a polynomial function. All right, so all these are horizontal lines, right? Horizontal line, horizontal line. So a horizontal line is considered a polynomial function because of the definition. All right, now let's look at some examples. So let's look at this. Note, oh, and by the way, I want to mention this. So remember in example 1, g of x here, g of x equals 3x to the 7. We said that was a polynomial function, right? Because it defines what a polynomial function is. It's one or more terms. The exponent's a positive integer, and my coefficient's a real number. We also know this though. Isn't this right here also a power function? So this example number 1, g of x equals 3x to the 7, is a polynomial function, and it's also a power function. So it is possible for a function to be both a power function and a polynomial function. So for example, here are examples of a function that's both a power function and a polynomial function. So you see, both of those are power functions, and both of those are polynomial functions. Look at the exponent, positive integer, or 0, which in this case is positive integers. All right, so just know it is possible for a function to be both a power function and a polynomial function. All right, now let's look at this example. So the question is this: which of the following are polynomial functions? Which of the following are polynomial functions? So number 1, a polynomial function? Is this function, negative 3x to the 5th plus 7x cubed plus 5x squared, a polynomial function? So remember, polynomial function, we're talking about polynomial here. Polynomial function, the exponents must be positive integers or 0. The coefficients can be any real number. So notice the coefficient here is negative 3, a positive 7, and a positive 5. What do you notice about the exponents? Positive integer, positive integer, positive integer. So the answer is yes. This is a polynomial function. Number 2. So we have 1, 2, 3, 4 terms. We have a finite number of terms. It could be one or more terms. The coefficients are real numbers, 1/2, a positive 2, a positive 7, and a negative 8. Now let's go to the exponents. A positive integer, 5 is a positive integer, but here's the issue. 2/3 is positive, but it's not an integer. So the answer is no here, and no because of 2/3, because 2/3 is not a positive integer. Okay, so that's not a polynomial function because of that exponent right there. All right, number 3. So is this a polynomial function? The answer is yes. It's one term. The exponent's a positive integer. The coefficient's a real number. So the answer is yes. It's also a power function, isn't it? It's also a power function. Notice it is also a power function. Number 4, is that a polynomial function? No, that is not a polynomial function because the exponent is negative. So the answer is no, it's not a polynomial function because the exponent is negative. It's a negative integer, right? It's an integer, but it's negative. So remember, a polynomial function, the exponents must be positive or 0. But notice, is it a power function? Yes, it is a power function. So it's not a polynomial, but it is a power function. Okay, number 5. don't let number 5 throw you off. You have 2x squared times this, right? All right, so remember, you got to remember something. And let me go ahead and do that here. I want you to notice, if you look at this carefully, if you distribute this, notice what happens. So I'm going to write this here. So 2x squared times x to the fifth plus 3x squared plus 5. If I distribute, I get 2x squared times x to the fifth, right? So when I multiply like bases, I add exponents. 2 plus 5 is 7. So that's 2x to the 7th. 2 times 3 is 6, so plus 6. X squared times x squared, 2 plus 2 is 4. Multiply like bases, add exponents. And then 2x squared times 5 is 10x squared. So this right here actually equals, I'm going to put that in a box here, actually equals 2x to the 7th plus 6x to the 4th plus 10x squared. And notice this is, all these exponents are positive integers. So the answer is yes, that is a polynomial function. Number 6, you have a square root. The answer is no. All right, and you may say, well, I think you could write a square root as a rational exponent. You could. You can write this. You can write this as 7 times x minus 8 to the 1/2. But the problem is your base must be the variable x only. So your base. Let me get to that definition again. So your base must be just the variable x. See, all these are x. X to the power, x to a power, x to a power, and so on. The other problem is this. 1/2 is not an integer, right? So the answer is no. And so this is not a polynomial function for the reason that this 1/2 is not a positive integer. All right, now I said something a while ago that I need to also clarify. So what if you had this? And this is going to be number 9. So I'll write this as number 9 right now. What if I had f of x equal 7 times x minus 8 squared? Okay, would that be a polynomial function? And the answer is yes. The answer is yes. Even though you see that x minus 8, you see a positive integer, right? Which means I can expand this because I know that x minus 8 squared means x minus 8 times itself. And so I can write this right here into this form where I have just x to a power, and then a constant. So watch what happens. So x minus 8 times x minus 8 is x squared. The outer and the inner combine to a negative 16x, and a negative 8 times a negative 8 is a positive 64. And so I get 7 times x squared minus 16x plus 64, which becomes 7x squared. And then 7 times a negative 16 gives us negative 112x. And then 7 times 64 is a positive 448. So notice f of x is this right here is a polynomial function because I can write, even though this base is not x, it's being raised to an integer power in which I can easily expand to look like a sum of terms. Okay, whereas this one I could not do that because notice this exponent, first of all, is not a integer, and it's not a positive integer. So the answer number 6 is no, since 1/2 is not a positive integer. But in number 9, it's yes. It is yes, because this is a positive integer, and I can expand it into that form, into a polynomial form. Okay? All right, so just keep that in mind. Number 7, same thing. Don't let this confuse you, because you can look at this right here. You can look at this, and you can rewrite this, couldn't you? So 3x cubed times 2x is 6x, and then 3 plus 1 is 4. So that's 6x to the 4th plus 6. And so is that a polynomial? Yes, it is. So the answer is yes. So be able to rewrite this into something that's recognizable. Just like number 9, be able to rewrite this into something that's recognizable. Here, you have to know right away that there is no way that this is a polynomial function because of that square root. I can rewrite a square root as a rational exponent 1/2, and 1/2 is not a positive integer. Number 8. Number 8, we talked about this before. Notice that in order for it to be a polynomial function, the variable must be your base. The variable is not the base here. The variable is the exponent. So this is no. In fact, this is an exponential function. An exponential function cannot be a polynomial function. Those are two different functions because of the base. In a exponential function, the base is a real number, whereas in a polynomial function, the base is a variable. All right, that was number 8. All right, and don't forget we did number 9, so this will be part of number 9 right here. So keep that in mind. Number 9. All right, and then finally, let's look at this example. And I think that should be enough to help you understand the difference between a power function and a polynomial function. All right, so the direction says this. For each function, indicate whether the function is a power function, a polynomial function, or both, because remember, we did talk about the fact it could be both, or neither. So number 1, g of x equal 3x to the 8th power. Is that a power function? The answer is yes. That's a power function, right? You have one term, and my exponent is a real number, and my base is a real number. But it's also a polynomial in it, because my exponent is a positive integer. So the answer here is both. Both. So you can say both. All right? You must use the word both. Don't say power and polynomial. Use the word both. I'm telling you what to use. Use both. Okay, h of x equals 3x to the first power minus 7. So this linear function is a polynomial function, right? So that's polynomial only. So you write the word polynomial. What about this one? We talked about that. So notice the base is not the variable. So you're going to say neither. And remember, this is actually an exponential, right? That's an exponential function. Exponential function. Number 4, is that a polynomial? Yes. Your exponent's 2, positive integer, 1 positive integer, and then x is 0, 0. So that's yes. We talked about that. So this rational function is not a power function, nor is it a polynomial. So we will say neither. Is this a polynomial, power, or neither? Well, if you look at the exponents, that's a positive integer, but here we have a negative integer, so it'll be neither. Neither. Number 7, absolute value. Remember the absolute value. Some students get confused about this. So remember the graph in absolute value looks like this, doesn't it? All right. But the problem is that in order for it to be a polynomial function, see where this point here, it's got to be a smooth turn. This is a sharp turn. You go here and then here. So you'll learn more about that idea in calculus. But the answer is no, this is not a polynomial function because of the absolute value. Absolute value functions are not polynomial functions. All right, so absolute value functions are not polynomial functions because of that sharp turn. You cannot have that sharp turn here. It must be a smooth curves, just like this. And a line is a polynomial function, right? You don't see any curves, but by definition, a line is a function, all right? A line is a function, although you don't see any curves like you would see when we normally talk about a polynomial function. But an absolute value function is not because of this turn right here. It's a sharp turn. All right, a sharp turn. So a sharp turn does not represent a polynomial function. All right. So the answer is no. No. Okay. And so that's it. So that is, let's see, let me go back to that first page. So that is the lesson on the topic of power functions and polynomial functions.